Welcome to Chapter 4. The topic of this chapter is probability. Understanding probability theory is essential for extracting information from data in EDA. Using probability theory, we can find underlying pattern in data and clearly show the pattern to our audience. By the end of this chapter, you will be able to explain statistical independence and apply it in computing conditional probability. Explain the importance of considering conditional probability using Simpson's paradox, and consider a binary classification problem using the Bayes theorem. Let's see this cross-tabulation table. It shows how many male and female workers are employed by each company. It is not so hard to see each company's size and whether each company employ more male or female workers. However, if we want to see the degree of male dominance or female dominance for each company, this cross-tabulation table is not so easy to see the tendency. Instead of frequency, we can input percentages to each cell. The character n in the furthest right column represents the total number. This cross-tabulation shows us clear information of how each company is male or female dominance. Proportional percentage represents probability. Oftentimes, probability shows us patterns and tendency more clearly than frequency. So, using probability is useful in EDA and other analysis. However, without knowledge of probability theory, we sometimes fall into some misunderstanding. To understand probability theory, we need to know the basics of set theory. So, let me begin by set theory. In set theory, a set represents a collection of elements that can be regarded as a single object. In the case of throwing a die, we can regard the pips as a set. And each of 1, 2, 3, 4, 5, and 6 can be regarded as elements. Here, a collection of 1, 2, 3, 4, 5, and 6 can be regarded as a single object, that is, pips of a die. A set is usually described by enclosing elements by curly brackets. According to the definition of a set, how we define a single object will affect what elements constitute the set. So, if we define a set as pips of a six-sided die, the elements are 1, 2, 3, 4, 5, and 6. But if we define a set as odd number pips of a six-sided die, the elements are 1, 3, and 5. Throwing a die is just a kind of behavior, but we can generate various sets from there. Each outcome of throwing a die is a numerical value. But a set can consist of non-numeric elements. For example, when we define a set as continent, it consists of 7 elements: Africa, Asia, Europe, North America, South America, Australia, and Antarctica. In this case, each element is not a number, but a category. Before going on to set theory, let's see the definitions of basic terms because they are a little confusing. First, as we saw in the previous slide, a set is a collection of elements that can be regarded as a single object. So, pips of a die can be an example of a set. An element is an object that is a component of a set. So, 1, 2, 3, 4, 5, and 6 are elements that consist of a set, pips of a die. And let me introduce the term experiment here. Experiment is any procedure that can be infinitely repeated and has one deterministic or randomly determined more than one possible outcomes. In the case of pips of a die, the experiment is throwing a die. Another term, event, is an outcome, is an experiment. So, in this example, each pip 1, 2, 3, 4, 5, or 6 can be the outcome of the experiment of throwing a die. Let's consider relationship between two sets using Venn diagrams. A Venn diagram is a diagram that shows the logical relation between sets. Let's consider a case of pips of a six-sided die. All possible elements are 1, 2, 3, 4, 5, and 6. Let's define set A as odd numbers. So we can depict set A by a green ellipse. And let's define set B as a greater than 3 and depict it by an orange ellipse. The event 5 is placed on the overlapped part of the two ellipses. The number 5 is an odd number and greater than 3. So we can say that the event 5 belongs to both of the sets. A set which consists of all elements that belong to both A and B is called the intersection of A and B. To represent an intersection, we can use a symbol cap. In this example, only 5 belongs to both A and B. So, the intersection A and B consists of one element, 5. A set which consists of all elements that belong to either A or B is called the union of A and B. To represent a union, we can use a symbol cup. In this example, 1, 3, and 5 belong to set A, and 4, 5, and 6 belong to set B. So, the union of A and B consists of 1, 3, 4, 5, and 6. To understand the term probability in data science, we first need to know the term random experiment. Random experiment refers to an experiment that satisfies the following two conditions. First, there are more than one possible outcomes. Second, the outcome is observable but cannot be predicted with certainty. Typical examples of random experiment include throwing a die and flipping a coin. An experiment is deterministic if it has only one possible outcome. So, what is probability in data science? Probability is a quantitative representation of the likelihood that an event occurs on a single trial of a random experiment. In a general notation, the probability of event A is written as P parenthesis A. For any event A, probability ranges from 0 to 1. In a probability, 0 means the outcome never happens, and 1 means the outcome always happens. In 1795, Laplace defined probability by this formula. It is known as classical definition of probability. Here, n is the number of outcomes favorable to A, and k represents the number of all possible outcomes. So, the probability of event A occurring can be defined as k divided by n. An important assumption underlying this formula is that all outcomes are equally possible. Let's see an example of pips of a die. Suppose a case we use a fair die, so each pip is equally possible. Let's define event A as getting a 1. Here, the all possible outcomes are 1, 2, 3, 4, 5, and 6. So the number of all possible outcomes is 6. So the probability of event A is 1 divided by 6. So it is 0.1666. If we define event A as getting an odd number, there are three outcomes favorable to event B. They are 1, 3, or 5. So the probability of B is 3 divided by 6. So it is 0.5. So how about the probabilities of A and B and A or B? First, let's see A or B by defining event C as getting 1 or 3. In this case, we can get the probability of event C by summing up probabilities of getting a 1 and getting a 3. So it is 0.33. Next, suppose a case we throw a die for 2 times and define event D as getting odd numbers 2 times in a row. So what is the probability of event D? Let's depict a tree diagram of this experiment. This experiment consists of 2 experiments, the first flip and the second flip. Both of them have 2 outcomes, odd or even. So, in total, there are 4 patterns of outcomes. And one of them is a case where we get odd numbers 2 times in a row. So, its probability of occurring is 1/4, 0.25. Let's consider the case of event D a little more. Let's name the event where we get an odd number in the first throw as O1. And let's name the event where we get an odd number in the second throw as O2. So, event D is the intersection of event O1 and O2. Event O1 is 0.5 of the total outcomes, and O2 is 0.5 of the O1. So, the probability of event D can be computed by multiplying the O1's probability and O2's probability. Let's consider another example. Probability that a student gets grade A in both algebra and calculus. Let's name the event as ACA. In both algebra and calculus, only 10% of the students can get grade A. Let's name events where students get grade A in these classes as AA and CA respectively. Similar to the die throwing example, we can compute the probability of ACA by multiplying AA's probability and CA's probability. So it is 0.1 by 0.1. It is 0.01. So we can say only 1% of the students can get grade A both in algebra and calculus. Is that true? Maybe not. Could you tell me why? It is a problem of statistical independence. If event A's occurrence does not affect event B's occurrence, event A and event B are statistically independent. On the other hand, event A's occurrence affects event B's occurrence. Event A and event B are statistically dependent. So, in the example of throwing a die, getting an odd number in the first throw does not affect the probability of getting an odd number in the second throw. So, they are statistically independent. On the other hand, in the example of a student's grade, getting grade A in algebra and in calculus may be statistically dependent. It is because students who are good at algebra are more likely to get higher calculus scores. If 2 events A and B are statistically independent, the probability of A and B's intersection equals to A's probability multiplied with B's probability. However, if A and B are statistically dependent, this equation does not hold.